Our beloved mango is composed of a fleshy inside and a thin skin. In the previous videos, you learned how to mathematically describe the inside using the interior and the edge using the boundary. So the interior and the boundary make up the whole mango. Now, we are going to challenge ourselves. How can we describe the entire mango, flesh and skin, using a new, completely different mathematical idea? In this video, you will see how to use this mango to intuitively think about the definition of a limit point and the closure of a set in n-dimensional Euclidean space. What is the definition of a limit point of a set? Let S be a subset of n-dimensional space. A point P in n-dimensional space is a limit point of S if, for every epsilon bigger than 0, the punctured open ball, so the open ball of radius epsilon without the point P, has non-empty intersection with S. In other words, there exists a point Q in S not equal to P such that the distance between Q and P is less than epsilon. Let's apply this definition to our mango. Like before, we will visualize our mango with a two-dimensional model. Think of it as a set S lying inside two-dimensional space. For this example, I want to emphasize that S will only be the dough and not the edge of the dough. Okay? And I'm also going to add a fourth point. So this extra piece of dough you want to consider as part of my set S. So we already have 3 different points in two-dimensional space from before. Point A, point B, point C, and now our new favorite speck of mango, point D. We will check if these are limit points of S. Look at the point A. Is this a limit point of S? Intuitively, yes. It is inside the mango, so it is actually surrounded by mango. So let's check that the formal definition matches this intuition. So for every epsilon greater than 0, the punctured open ball centered at A has non-empty intersection with S. This cookie cutter will be our open ball as usual, and when I place it, I'm going to place it with A at the center. However, to think of it as punctured, you want to imagine that the point A is removed. Now looking inside the open ball, I can see some mango inside, ignoring the point A itself. In other words, the punctured open ball has non-empty intersection with S. So does this mean A is a limit point? Not yet. We technically need to check every epsilon bigger than 0 as always. I can place a smaller punctured open ball at A. Looking inside the smaller punctured ball, there is some mango inside, again ignoring the center point A. I can try an even smaller punctured open ball, so imagine the point is gone, and I still see the same thing. There is only mango inside actually, with such a small ball, and once this happens, I can guarantee that every punctured open ball inside this one will still have mango. This is going to prove that A is a limit point of S. Remember, we always have our equivalent perspective. These cookie cutters allow us to zoom in on the point. A smaller radius means we are zooming in more. We confirm that this point is a limit point because no matter how much we zoom in, we will always see nearby points inside the mango, not including the center itself. This idea gives an informal way to interpret limit points. A point P is a limit point of S if no matter how much you zoom into P, you always see points inside S, not including P itself. Now, let's go back to our 2D mango. Is the point B a limit point of S? Intuitively, yes. It is on the edge of the mango, so there's always some mango nearby. So let's check the definition as always. For every epsilon bigger than 0, the punctured epsilon open ball centered at B has non-empty intersection with S. So here's my open ball. I remove the point, and we can still see there are points inside S, inside this ball as well, which is not including the actual center itself. This smaller punctured open ball at B also has points inside S. And so does this smaller ball. Another way to think about this is that if you are an ant who can only travel inside the mango, you can keep approaching this point B, the edge where the skin is, as close as you want, but you never need to reach B itself. So this heuristically proves that B is a limit point of S. And notice an important point. B does not actually belong to S. Remember, it's on the edge, which we said was not part of S. But it's still a limit point of S. Is the point C a limit point of S? Intuitively, no. It's outside the mango, so there's no mango nearby. To check this, we have to negate the definition. So there exists an epsilon greater than 0 such that the punctured open ball centered at C has empty intersection with S. This punctured open ball, right, with the point at the center removed, as usual, has points outside the mango, but it also has a few points barely inside, inside the mango. So this doesn't prove anything for us. Now if I place this smaller open ball, again punctured, now there are no points inside the mango and inside the ball. This proves that the punctured open ball centered at C is empty for this choice of epsilon. This proves that C is not a limit point. Finally, there is a fourth point to consider. Remember this speck of mango that flew off to the side, very sadly, all by itself? We are treating this as a single point D in two-dimensional space. So is D a limit point of S? This situation's a bit weird, but the answer is no. It is part of the mango, but it has no mango nearby. Let's check the definition to be sure. We need to show there exists epsilon greater than 0 such that a punctured open ball centered at D has empty intersection with S. So let's start with this open ball. So I'm putting an open ball centered at D, but remember it's punctured, so I'm going to remove the center. Now if I look inside this punctured open ball, there is actually some mango right over here, barely on the inside. If I just tilt that a little for you, you can see a bunch of mango. This means this open ball will prove nothing for us. So let's try a smaller open ball. So I'm placing this smaller punctured open ball. Again, remember, the center point is removed at D. And now, this punctured ball has no points inside the mango because D itself does not count. So the punctured open ball centered at D intersected with S, the whole mango, including the speck, is empty. This proves that D is not a limit point of S. In fact, points like D are what we call isolated points of S, which by definition are points of S that are not limit points of S. These examples have prepared us to define the closure. Let S be a subset of n-dimensional space. The closure of S, denoted S bar or CL of S, is the union of the set S and the set of limit points of S. How does this apply to our mango? Recall we checked that A and B are limit points of S, whereas C and D are not. Continuing these ideas, any point inside the mango or along the edge will be a limit point. Any point outside the mango or an isolated speck will not be a limit point. Reflecting a bit more, this observation spawns a discovery. The closure of S is both the inside and the edge of the mango. Remember, the inside corresponds to the interior of S, and the edge corresponds to the boundary of S. So, equivalently, the closure of S is the union of the interior and the boundary of S. This makes a really nice theorem relating limit points, interior points, and boundary points. All of these ideas can be applied to our 3D mango. The skin is the boundary, the flesh is the interior, and the entire mango is the closure. Thanks for watching this video series exploring the interior, boundary, and closure of a set using a mango as a metaphor. Now enough talk about mangoes. Time to eat one.